parallel plate capacitor is the simplest form of a capacitor. It consists of two parallel plates separated by an insulator. When the capacitor is uncharged, the number of positive charges on each plate is equal to the number of negative charges on that plate. If you connect the capacitor to a simple DC circuit, such as the one shown, which contains a resistor, a battery, and a switch, at the moment you close the switch, a current flows in the circuit, which is resulting from the negative charges moving from the right plate in this example and accumulating on the left plate. This leaves an excessive amount of positive charge on the right plate and an excessive amount of negative charge on the left plate. As this process continues, more and more charge accumulates on both plates, and the current reduces over time until it stops when the capacitor becomes fully charged. This occurs when the voltage across the capacitor becomes equal to the voltage across the battery. The ratio of charge to voltage is always a constant value which equals to the capacitance C. And this is correct at any time during the charging process. The capacitance is measured in farad, which is the unit of coulomb divided by the unit of volt. Now, if you study the charge versus time, you'll find that we started with zero charge and we ended up with a fully charged capacitor. In fact, the charge versus time looks like an exponential growth curve. This curve starts from zero and ends at the maximum charge. In case of voltage, the same thing applies. We started with 0 volts across the capacitor, and this voltage difference increases until it reaches the maximum voltage, which is once again equal to the voltage of the battery. If you study the current versus time, however, you'll find that we always start with a maximum current, and this current decays over time until it reaches 0 when the capacitor becomes fully charged. In fact, the current versus time curve is an exponential decay curve. Let's define what's called the time constant of the circuit. The time constant is defined as the time required for the quantity in the exponential growth curve to increase from 0 to 63% of the maximum value. So as an example, if you have a maximum voltage of 10 volts, then 63% of this value is 6.3 volts. So the time constant in this example is the time required for the voltage to increase from 0 to 6.3 volts. The definition is a little bit different for exponential decay curve. In this case, it is defined as the time required for the quantity to decrease from the maximum to 37% of the maximum value. Now, back to our example, if you disconnect the battery from the circuit, then the capacitor will maintain its charge, and this is its purpose. It stores charge. Now, to discharge the capacitor, you can close the circuit, close the switch, and then you'll see that a maximum current flows in the opposite direction, resulting from the motion of negative charges from the negative plate to the positive plate. Once again, this current starts at maximum value and then decays to 0 when the capacitor becomes discharged. The charge versus time for this case is an exponential decay curve because we started with maximum charge and this charge decays to 0 after some time. For the voltage, it's the same thing. The voltage across the capacitor was equal to a maximum value, and then it decays over time until it reaches 0 when the capacitor becomes uncharged. For the current, it's the same thing because we started with maximum current and this current decays to 0 when the capacitor became uncharged. Here is a comparison between the two cases. And notice the difference between the definitions of the time constants for each quantity and each case. Always, whenever you have an exponential growth function, the time constant is defined as the time required to increase from 0 to 63% of the maximum value. And when you have an exponential decay function, then it is defined as the time required to decay from the maximum to 37% of the maximum value. Also note that the current is always an exponential decay curve. The time constant of each circuit actually depends on the resistance and the capacitance in your circuit. It is given by tau is equal to R times C. We will use this relation to find the capacitance in our circuit experimentally. In our experiment, we will concentrate on the voltage versus time, charging and discharging curves. You will connect a circuit like this one with a little difference. Instead of the battery, you will connect an AC power supply that has a square wave. Now this is how the square wave is like. It changes between maximum and 0. So to see what happens on the capacitor side, when the power supply signal is at the maximum, this is equivalent to having a battery connected to our circuit, which is equivalent to the charging circuit. So you will see that the capacitor is being charged when this is the case. When the power supply signal, however, drops to 0, this is equivalent to having the capacitor connected in the discharging circuit, and you will see that you get a discharging curve. You will see a number of cycles of charging and discharging on the screen of your oscilloscope. So you will zoom into one of these cycles in which you have charging and discharging curves. And this is how it will look like on your oscilloscope screen. So to find the time constant, again from the definition, it is very simple. You will place the first cursor at the beginning of the charging curve. Place the second cursor so that the voltage at the second cursor is equal to 63% of the maximum voltage. The time difference between the two cursors is basically the time constant of your circuit, which will be displayed on the screen of the oscilloscope. You will also study the same thing for the discharging curve. So you will move the first cursor to the beginning of the discharging curve and move the second cursor so that the voltage at the second cursor is equal to 37% of the maximum value. The time difference, once again, is the time constant of your circuit, which is going to be displayed on the oscilloscope screen. A larger capacitor will have a slower circuit. So you will notice that when you connect a smaller capacitor, you'll get a steeper curve, like the one shown. Here is a comparison between the two. Notice that when you have a smaller capacitor connected, the time constant is smaller, which means that smaller time is required to reach the maximum voltage. In this circuit, the two capacitors shown are connected in series. So the charge on one of the capacitors is equal to the charge on the other one. However, the voltage difference across both capacitors, which is the total voltage, is equal to V1 plus V2. These are the properties of the series circuit. If you combine these two equations with the help of Q equals C times V, you will find that for a series combination, 1 over C of the series is equal to 1 over C1 plus 1 over C2. Of course, at the end, do not forget to calculate C itself. In case of capacitors in parallel, however, the voltage across the first capacitor is equal to the voltage across the second one. However, the total charge is equal to Q1 plus Q2. Once again, combine these two equations by the help of Q equals CV equation. You'll find that for a parallel combination, the equivalent capacitance is equal to C1 plus C2.
Here is the circuit diagram that we want to connect for this part of the experiment. Now notice that these wires go to channel 1 of the oscilloscope and these two go to channel 2. They are in parallel, so we will leave them to the end and we will connect the main circuit, which consists of the resistor, capacitor and the power supply connected in series. So let's start with the power supply side, and this side is connected to the resistor. So we will take a wire connected between the positive side of the power supply to one side of the resistor that we will use for this part. Now, the other side of the resistor is connected to one side of the capacitor. Here is the other side of the resistor. And here are the two capacitors. Let's start with C1. So we will connect this side of the resistor with one side of the capacitor. Now, according to the diagram, the other side of the capacitor goes back to the power supply. And notice that we have a ground symbol here, which means that this should be the negative of the power supply. And that's why we started with the positive side. So here is the negative of the power supply connected to the other side of the capacitor. Now it's time to connect the two channels of the oscilloscope. So we will connect channel 1. I can get a black wire. So channel 1 is connected across the capacitor. So here is the capacitor, and notice that this is the ground side. So the ground side has to be connected with the ground side of the oscilloscope. And this is channel number 1, as you recall from the previous experiment. Now, the other side of channel 1 should be connected to the positive, the other side of the capacitor should be connected to the positive side of channel 1. Now, for channel 2, it has to be connected across the main power, which basically goes between the black to the black, and let's tilt this, and the blue to the positive side. And this is the connection for the main circuit of part 1. Now notice that for parts 2 and 3, we have to switch between C1 to C2. So we'll have to remove these two wires and insert them in C2. And then after that, we connect C1 and C2 in series, and we will show you a picture of that connection. And also, finally, we will connect them in parallel. Parallel connection is very simple. You just take two wires from C1 and connect them to C2, just like this, two wires, okay? All right, so we will turn the power supply on. Now, as you can see on the screen of the oscilloscope, we already set the signal generator to a square wave. Notice how when the signal generator is at this voltage, this means that the capacitor is being charged, okay? That's why you see a charging curve. When the voltage of the signal generator is 0 volts, the capacitor is being discharged, and we see the discharging curve. Now, what we would like to do is to measure the time constant of the discharging curve. So let's zoom in. I think this is a good scale right here. Okay. Now, remember that the time constant is the time required to go from the maximum voltage down to 37% of this maximum voltage. So the best thing to do is to hide this input signal, because we're working on the capacitor signal, and then turn the cursor function on and use the time cursors. Now we're going to set the first one, cursor number 1, at the beginning of the discharging curve right here, okay? Now, notice that the reading of cursor number 1 is 1.92 volt, and it is fluctuating a little bit because of the noise coming from everywhere. So let's take a single snapshot of the signal. Now it is more stable. Now we have cursor 1 at 1.94 volts. So let's calculate 1.94 multiplied by 0.37 because remember the time constant is again the time required to go from the maximum, which is 1.94, to 0.37 of this maximum, which is, if you use your calculator, it's 0.72 volts, 0.72 volts, okay? So I'm gonna place cursor number 2 at the 0.72 volts, which is 720 millivolts, because notice how it is displaying everything in millivolts. And the closest, looks like the closest I'm getting is, I believe, 700 millivolts, okay? So this is the closest to 0.72 volts, right? So we're gonna leave it here. And now, again, the definition of the time constant is the time required to go from the maximum to 0.37 of the maximum. So it's the time required to go from 1.94 volts down to 0.7 volts. The time difference between the two cursors represents directly the time constant, which is in our case displayed by the oscilloscope as 180 microseconds. So this is your time constant.